All right, good morning. Today we will talk about the emotional EMF with the limitless source of electrical energy. Earlier we talked about and learned that how we can generate the electric current either by changing the magnetic field, or in either case we're changing the magnetic field either by moving the magnet or by changing the area of the cross section, which means by changing the flux. Now, once we understood that the electricity induced current can be induced by changing the magnetic field, now is the time to understand that how we can have the motional EMF, electromotive force, induced current, with the as a source of limitless electrical energy, the continuous electrical energy. So here is a setup for this. We have a conducting rails connected with the electrical bulb on one end, and the other end of the rails is open. Now, in this open end, I place a conducting bar. Now, there is a permanent constant magnetic field applied on this setup, which we can see with this cross, and which means this external magnetic field is into the paper. Now, when I move this conducting bar, which has a positive and negative charges, now I move the conducting bar. So when I start moving it with an applied force towards right, what is going to happen? Let's see, the negative charge, the electron in the in this conducting bar also, which is part of this conducting bar, will also start moving as the whole setup moves. So as the bar moves, as the bar slides over here, so the electron which is residing over here will also be moving, just like we are sitting in a train or a car. When the car moves or the train moves, the whole system moves, the object sitting inside the train or the car moves. So the same thing is here. The electron, which is the part of the conducting bar, also moves when I apply a force F towards right. So as I do that, since this is an electron, so for the positively charged particle, we use the right hand where the fingers point in the direction of the moving charge, and when I curl my finger toward the direction of towards the magnetic field, and thumb will point the force. So here is a negative charge, so I can use my left hand where the fingers point in the direction of the moving electron, and the magnetic field is applied magnetic field, the external magnetic field is into the page, so I curl my finger towards the page and the thumb will point in the direction of the force. So what it means, that when I move the bar, the electron will have a magnetic force which will make the electrons move in the bar towards down. So here is the force on the magnetic force on the charge. Alright, now once we have that, we know the force is equal to force on the charge Q when it is placed in an external magnetic field. It is equal to Q times V times B sine of theta. So the electron, as I said, is moving towards the lower end of the bar. Now the conductor has both positive and negative charges. If the electron moves downward, so positive charges are accumulating upward. So it means if the current due to electron is going downward direction, so the current due to the positive charge is in the opposite direction. So the negative charge is in one direction, positive charge is in another direction. So one end of the bar will become negatively charged, other end becomes positively charged, right? Now, as we see, the lower end is the negatively charged of the bar and the upper end is the positively charged. Now, if the one end of the bar is the negatively charged, other is the positively charged, it means the two ends of the bar are at two different charges. What it means? It means we have a potential difference between the two ends. Alright? Now let's see. This bar has a length of L. So the L is the distance between the two ends of the bar. Now, not only that, due to these positive charges, there will be an electric field. And due to positive charges, the electric field lines going outward. And due to the negative charges, the electric field lines coming inwards. So now we have this separation of charges created an electric field which will pull the charges back. So this negative charge, the negative charges most accumulated here on this end, not accumulated, but this end, and the positive on the other end. So although they are moving, flowing, the current is flowing. So let's consider the motion of this negative charge, right, which is moving. So this negative charge is experiencing a force between the two ends. So two electric fields. So here is an electric field due to the positive end of the bar. Here is an electric field due to the negative end of the bar. Since this is a negative charge, this negative charge being repelled from these negative source charges, and this positive charge will going to attract them, right? So as a result, you see the charge will feel like hanging, and it experiences two forces. One is the force which is the electrical force, which is equal to Q times E. Other, the force, since it is placed in an external magnetic field and on a bar, a rail, on the conducting bar, which is the whole setup is in an external magnetic field as over here. Now, what is going to happen is these two forces try to balance each other. So here is an electrical force, here is a magnetic force. When I equate the two, so the two forces, electrical force is on the charge is equal to magnetic force on the charge, right? So which is equal to Q times E, and this is equal to QVB, and the sine of theta, of course, and let's say the angle between the magnetic field vector, which is pointing inward into the page, and the velocity towards the right, which is 90 degree. So sine of 90 degree is equal to 1. So which means I can write here QVB is equal to Q times E. Now I cancel the Q's, and E is equal to V times B. So this is, let's put this a tilted V, so that this is the velocity to differentiate between the potential. Now keep in mind, the potential difference is, we learned in the previous chapter, the potential difference is also has a relation with the electric field time, the distance between the 2 points. Here, the distance between the 2 points, which is the distance between the two ends of the bar, is L. So if I do that, so this is L, positive, 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 and negative, negative, negative. So this is the distance L. So it means the potential difference delta V is equal to E times L. Alright? Now the EMF, electromotive force, which is basically a potential difference between the two ends. So I can write the EMF is equal to the potential difference between the two ends equal to electric field times the distance between the separation between the two charges. Now, from this above relation, we also see electric field. From this relation, we found out electric field is equal to velocity times the magnetic field. So now I replace this electric field over here with the magnetic velocity times the magnetic field. So I got a interesting relation for the EMF is equal to, give me the EMF, electromotive force or motional EMF is equal to V, velocity times the magnetic field times the distance, which is the length of the bar. Now, if I reverse the motion, then the polarity of the potential difference will be reversed. When I say reverse, it means since I was pulling the bar towards right, instead of pulling it towards right, I will start pushing it towards left. So which means I reverse the polarity. So the polarity of the potential difference will be reversed. So in that case, you might have charges moving in the accumulated in the opposite direction. So the direction of the EMF will be reversed. So that is just the polarity is changing, nothing else. But still we have a current over there, induced EMF over there. All right. So now let's also assume that this moving bar has a zero resistance. An ideal situation, although there is no such thing ideal resistance, zero resistance. It's only ideal. So let's we assume that the bar has a zero resistance. We don't want to deal with too much resistance over here. Now this bar, conducting bar is on the rail, and of course these rails are connected permanently with this T2 wire, which has a resistance R already over there. So that is why we have zero resistance on the bar. Now I applied the force on towards right, and the bar moved with the velocity v towards right. Now again, having done that, the free charges in the conducting bar will experience a magnetic force, right? As we saw earlier, so that magnetic force is equal to the electrical force over there. So this force, magnetic force, sets up an induced current, because due to this magnetic force, the charges will start moving and it will push the charges, and as well as the induced EMF will be there. So these free charges will experiencing a magnetic force along the length of the bar, rather than this way. This is going in this direction. Okay, it's not. So as a result, this force will let the charges move in the circuit. As a result, the current will be produced. So basically, this picture is a better representative of that whole system. So the charge moves because of the magnetic forces applied over there. Okay. Now, here, let's go further. Let's apply this on the Faraday's law. Now, keep one thing in mind, that in this previous slide it shows the force on the left hand side. That is because of the Faraday's laws and the Lenz's laws combined. There is a cause and effect that can be explained, but right now let's focus on that the magnetic force produces an induced current over here. Okay. Now let's see, by applying the Faraday's law. What is the Faraday's law? We learned the Faraday's law says the magnetic flux is equal to the magnetic field, applied external magnetic field, times the area. through which the magnetic field line are crossing. Phi is equal to B dot A. Okay, and this is equal to B times A cosine of the angle between the magnetic field vector and the normal to the area vector. Now let's apply this over here. Okay, now here is the situation. This is the area. Okay, this is the area. Now the magnetic field lines are into the page. The normal to the area is also that direction. So which means the angle between the normal to this area is, and the magnetic field vector is 0, right? So here is the magnetic field lines, and the normal to the area is also this direction. So the angle between the magnetic field lines and the normal to the area is 0. So now B times A cosine of 0 is 1. Now let's deal with the area. So what is changing in this case? The area is changing because we are moving the bar. Alright, as we move the bar, let's say that initially the bar was at this point. Now I applied the force, the bar moves from here to here. So this distance is delta x between the two positions of the bar. Now the length of the bar remains same. So it means I can write this area is equal to L times the delta x. So let's do a little bit of math over here. So phi, the magnetic flux, B times area. Now let's see B times A, because cosine of 0, which is 1. Okay, so area is L times delta x. Okay. Now EMF induced, according to the Faraday's law, EMF induced is equal to change in the magnetic flux with respect to time. Alright? Now, let's see the change in the flux. I plug that in over here. So that is going to give me BL delta x over delta t. Alright? So what is delta x over delta t? If we know from the basic definition of the velocity, change in displacement over with the time. Alright? So it means I can replace this with BLV. So this is nothing but velocity. So EMF induced is equal to BL times V. Now this is the EMF induced. Now I want to know the current induced. So what I'm going to do in order to find this induced current, so all I'm going to do is use the Ohm's law. And what does the Ohm's law tell me? So the Ohm's law says here V is equal to I times R. So here, which is EMF, is equal to I times R, and I is equal to EMF induced divided by R, and R is the resistance over here. Okay. Now EMF induced is BL times V. I can write BL times V divided by R. So this is the induced current. Okay. Just came from the Ohm's law. Alright? So let's make some work out some example over here. Apply this, whatever we have learned so far. So let's see what this example says. So in this circuit here, given to you. So a flashlight bulb is lighted by a bar pulled along a stationary rail. So bar is being pulled towards right. Now the bulb has a full brightness of power P of the bulb at the V of the bulb, whatever is the voltage crossing. What is the velocity of the bar needed to obtain the full brightness of the bulb? So it's a nice bulb which can be fully brightened. So it's a new bulb. What force will be required to pull the bar? Ignore the friction. So let's not deal with the friction over here right now. So only the bulb has a resistance in this circuit. So we know the power, we know the velocity, the voltage, the potential drop across the bulb. We know the magnetic field B applied, and then the length of the bar is given to you in centimeters. Make sure convert everything in a same system of units. So what we know from here. All right. So few things are needed in order to find out the velocity, first of all. So how do we find the velocity? So we know the EMF induced, which is the voltage, okay, is equal to B L times V, right? We learned that earlier. Now from here I can calculate the velocity, which is equal to the potential V of the bulb, right, divided by length L, which is, this is the length L, okay. So the length L, capital L or little L, that doesn't matter. So let's use the little L. So this is going to be little L times V. Now if I plug in all the numbers, I will get the velocity, which is going to be 166.667 meters per second. That's a lot of velocity, okay? So you can generate a lot of current here. Now what else we want to find out? The force of the pull, right? How much force is applied? So we know that we learned that the force of the pull is equal to the magnetic force, right? Because of how much you pull, that is equal to the magnetic force, right? When magnetic force will be generated. So more the velocity, more the magnetic force you generate over here, more the flux will change. So that is why I can write force of the pull is equal to the magnetic force. Now, what is this magnetic force? This is equal to V times, here we talked about that, V times L times B. All right. So the magnetic force, since there is a current I, we know that this is equal to, let's write it here. So that is the magnetic force, I times L times B, because current I flowing through the length L in the current carrying, it's now just like a current carrying wire in an external magnetic field, right? So this is equal to the applied force. Now I can write this, magnetic force is equal to the applied force. Add it here. Now from here, I times L, I is equal to nothing but V over R from the Ohm's law, okay? Using Ohm's law. Ohm's law, V is equal to I times R, right? Now, I can replace this V over R times L times B. Alrighty? So, now, what we can do from here? So, let's look at that. This is equal to V over R. So, I is equal to, using Ohm's law, V over R, and we know that the velocity of the bulb, the potential difference across the bulb is equal to velocity times the length times the magnetic field. All right? So let's do the following now. So let's do the following. I have to do a little bit of writing here. Alrighty, so potential difference across the bulb is equal to velocity of the bar of the length of L of the bar times the external magnetic field. Now, the force of applied force or the force of the pull, which is an applied force, is equal to the magnetic force, and the magnetic force of the current carrying wire in an external magnetic field is I times the length of the wire times the external magnetic field, and of course there is an angle theta, sine theta between them. If you remember, the magnetic force is equal to I times L times B. This is equal to I LB sine of theta, and theta is the angle between the current and the magnetic field, which is 90 degree over here, and sine of 90 is 1, so which means this is equal to 1. Now, I use this, the force of pull is equal to I, which is using Ohm's law, I is equal to V, the potential difference of the bulb across the bulb divided by the resistance provided by the bulb. So I can replace this with that, and it will be, well, potential difference across the bulb divided by the resistance times the length of the bar and the magnetic field. And now we know the magnetic potential difference across the bulb is this, right? So replace this over here, then we will get this is equal to V times L times B divided by R L times B. Alrighty? So from here, it's a little bit of mathematics you have to solve here. Now this is equal to V is equal to L square B square over R. Alrighty? So that is what you have over here. Alrighty? V F pull is equal to V square V L square B square over R. Alrighty? Now, what we know? We do not know anything about the resistance R. Alright? Now that's the problem. So what we know that in time we are given the power. Alright? Power dissipated across the bulb. So what I'm going to do is the following. Here we use the power of the bulb is equal to V, the potential difference across the bulb, square over R. Alright? So I can use that. Replace R with this. R is equal to V square of the bulb divided by the power dissipated across the bulb. Alright? So now, again, the potential difference, we can use this potential difference across the bulb. So we are given the potential difference, that's right. And actually we don't need to convert this to the velocity, never mind. So let's keep it as it is. So let's do the following. So I have V of the bulb. You can use the velocity, that's fine, there's no problem with that. L times B over R. Okay, now R is equal to this. So I'm going to replace this V of the bulb. L times B divided by, instead of R, I can write V, a potential difference across the bulb, square divided by the power dissipated across the bulb. Alright? Now, this power dissipated, I can move it. Let's take the power dissipated at the top. So now, and also I can cancel out one of the potential references here. Right? This will go with this square. So as a result, I end up with the power dissipated across the bulb is the times the length of the conducting wire times the external magnetic field divided by the potential difference across the bulb. Okay, so this is the pull force. All right, there you go. So that's what you want. Okay, we don't need to do this step. Okay, we can go directly from here to, don't need this step. You can use this step, there is nothing wrong with that, because then R will be, you can also take it in terms of the velocities, because we calculated the velocity already. That's fine. So you don't need to do more complicated way. So there will be 2 extra steps, that's okay. Now the answer should be same, there is no change in the answer. So now I just simply plug in the numbers and I get the pull force is equal to 9.009 Newton, which is 9 millinewton. All right. Now, we learned that the process where we can generate the EMF, induced electromotive force, and the induced current, while we change the magnitude of the magnetic field passing through the cross-sectional area, either by changing the magnetic field or by increasing or decreasing the area through which the magnetic field is passing through, which means the magnetic flux, change in the magnetic flux. Alright, now let's see what happens when the orientation of the loop is changed relative to the direction of the magnetic field. So we can change the orientation of the loop. So now that will lead to a very important implication, which is the generators. The generator which generates the current. Now, you see, instead of having the loop as it is, so either we are increasing or decreasing the area of the loop, right? So whether I was increasing or decreasing, the area of the loop. Now, instead of doing that, I keep the loop same, but what I'm going to do is inside the permanent magnetic field, I'm going to change the orientation of the loop. Alright? When I change the orientation of the loop, what is going to happen? Alright? That will lead us to the important implication, as I said, is the generators, which used to generate the electricity. Now, let's look at that. So I have a rectangular loop over here. Okay, and of course there is a mechanical process through which you change the orientation of the loop. For example, here I have this process. In this process, this is the magnetic field, which you see the red and the blue bars. So there is a magnet over here. So there are magnets in the side dash, the blue and the red area. Now I have this conducting coil inside that, and this conducting coil, which can be seen over here, this conducting coil is moving, right? I change the orientation of this coil, right? Here are the magnets, okay, and then this conducting coil. Now, how do I change the orientation of this the loop? Is just by rotating. I do some mechanical work. If I do some mechanical work by rotating here, and you see there will be this light bulb will be lightened up. Okay? And if I do the other way, now the green bulb will be lightened up. Okay? So that is how you can change the orientation of the loop. Okay? Now let's do the same thing here. So I have this loop which has the sides A, B, C, D, and C, D, and B, C, and D, A. Now if I look at the sides B, C, and D, A, these are so the current will be generated only through these sides, because the other two sides, B, A, and C, D, they are really not, the flux will not be, the current EMF will not be generated through that. This is the two sides parallel to the, perpendicular to the magnetic field over here at this point. So now EMF is generated only in the side B, A, and C, D. Alright? Now we know the EMF generated in the both sides will be same, alright, the same wires. So the EMF generated, because there will be L times V perpendicular. Now if I move this coil, you see this is the velocity vector. Now if I draw this velocity vector is in between the two coordinates. So which means this is an angle theta over here. So I will make the y and x component. So this is the parallel component and this is the perpendicular component. So the parallel component is going to be v times cosine of theta, and perpendicular component v times sine of theta. Now v times cosine of theta, theta is the angle between the velocity vector and the magnetic field, the 90-degree angle. So that is the velocity is 0. So that's not be useful over here. So that is why we only use the perpendicular component. So the EMF along this side and EMF on this side, B times L times V, which we learned earlier here. Okay, the potential difference is equal to V times L times V, which is the EMF. Now it is being generated on the two ends of the same coil, so which is the same. So I can add them up, the total EMF generated in this coil. So that is equal to total EMF generated is 2 times this EMF plus this EMF, 2 times B times L times V, perpendicular component, which is sine V times sine of theta. Alright, so this EMF across this B across side BC and AD is same. Now, since this loop is rotating, as you see over here, the loop is rotating. So it means there is a rotational component of a rotational velocity is there, all right? So we got to take into account the rotational velocity over here, all right? Okay? So due to this, we have to take into account the rotational velocity. And we know the rotational velocity, which is the angular velocity. This is theta is equal to omega times t, the angular displacement over time. And linear velocity and the angular velocity are related to each other by the relation. The relation is v is equal to r times omega. So the rotational velocity is omega and rotational displacement is theta. So we learned in physics 1. So theta is equal to omega times t, and v, the velocity v, is equal to r times omega. Alright? Now, what is r over here? This is the distance from that point of rotation, the axis of rotation, which is a by 2 over here. So this is equal to a by 2 omega. V is equal to a by 2 omega. Now the EMF, total EMF is equal to 2 times B times the length of the one end of the rod, the wire. So one end of the rectangle, L times V perpendicular, which is V times sine of theta. Alrighty? Now, from here, let's relate this with the angular velocity. 2 times b times L a by 2 omega sine of theta. Alrighty? So, you can simplify it further. Cancel out this 2. E is equal to b times L times a omega sine theta. And L times a is simply the area of the coil. So, which means I can see here, this length is L, area this side is A, so the total area of the rectangle is L times A, which is area represented with the letter, capital letter A. I can write B times A omega sine theta. Now, here we are talking about one coil, and if you look at this, there can be more than one coil, so I have several coils over here, turns, okay, number of turns, so which means the n number of coils over here. So let's say if there are n number of coils, so EMF is equal to n times b times a omega sine theta. Alright? And now theta is omega t, right? You can also write this in terms of the omega t or theta, whichever. You also write omega t over here instead of theta. But keep in mind, you see, now this theta depends on what happens. So you see, when this rotates, this generator rotates, it is going to generate the current, alright? So the cycle of the current changes, right? So not for the direct current. Direct current is unidirectional current, but we also generate the alternating current. And you see the alternating current, you see the flux is max over here goes to 0 when it's rotating, and when it reaches to the parallel over here, so which means the normal to the area and the magnetic fields are perpendicular to each other, so flux is equal to B dot A cosine of theta. So that means B dot A, which means B times A cosine of theta, and if the angle between the normal to the area vector over here and the magnetic field lines, which are perpendicular to each other, is 90, so cosine of 90 is 0, so the flux is going to be 0. So there is no flux over here, then no EMF generated. Remember, EMF generated from the Faraday's law is the change in flux with the time. So no flux, no EMF generated. So that is what you see, the flux as a function of time. So 0 flux over here. Now it goes towards the negative side. So when it keep rotating, now it keep turn on the other side. So it means the normal to the area and the magnetic field vector, they are making an angle of 180 degree against each other. And then the flux will be max on the negative side. Then it goes to this point where the flux is again 0, because normal to the area and the magnetic field vector are 0. Now again here, so the maximum. So it tells you the theta, the angle theta, okay? So if you look at this, the angle theta is here. The flux is max, and theta when this is 90 degree, okay? This area is 90 degree. This area vector and the magnetic field vector are aligned, or parallel to each other, okay? Or in other words, you can say that the sine theta is 90 degree, because here this area vector and this area and the magnetic field, normal to the area and the magnetic field are in the same direction, but this plane surface of the area and the magnetic field, they are 90 degree to each other, okay? So this is the maximum flux. Then here, the normal to the area and the magnetic field are perpendicular to each other, or so the surface area and the magnetic field lines are aligned, so that is a 0 degree angle between them. So this is 0 flux and maximum flux, 0 flux and maximum flux. Alright? So this is how the EMF is generated. Now Lenz's law also tells us the cause which generates the EMF. So always the effect of the cause is always to oppose the cause, to keep the flux constant through the coil. So that is how it will be done. So the flux will be met at 90 degree, all right, here. And when sine theta, this thing is 90 degree, or it is equal to 270 degree, right? 270 degree means, so you have here the 90 degree, so then 180, here is 270, right? Okay? All right, so this is how we generate the EMF. Now, the generators work on the same principle. With the generator, you can generate the alternating current or the direct current. So the only difference between the two is that there is a contact to the rotating loop are made by the split ring. So the split ring, what it's going to do is, so here is the slip circle rings, so that you have continuous generation of the current. Now here the cycle will change, okay? So it will not rotate, it will not flip basically. So it will be all the time changing it, right? So that is the only difference, that one has the split rings, the other has the continuous. All right? All right? So that is the difference between the alternating current generator and the direct current generator. All right. Now there are implications to that. So this is the electric current generator. This is the simplest one. So you have this, the parity plates and the spoons hooked up on that, and then you see if you throw the water with something, with the water hose or a little knob, so then these spoons like this, they keep moving, so they will rotate it, and as a result you can hook up this valve to this, and as a result there is a coil in the external magnetic field, so the current will be generated, and you see the bulb is lighted up. Alrighty? So we can do the same thing with the burner. So the nuclear power plants also, we have the heat generators, and then all it is you have to rotate. The wind generators are also the same principle, the power winds. So the wind, the natural wind generates the cycle and rotates the cycle, and this is then all you have is the coil in an external magnetic field, so then the coil rotates, as a result the electric field, the current is produced. So in this case, what is going to happen, in the case of the electrical motor, we supply the electrical energy, and then this electrical motor, due to the electrical energy, passes through it, and then this coil is placed in an external magnetic field, so the force is produced, the magnetic force will rotate the rectangle. So you can do, by supplying the electrical energy, you can do the mechanical work on the other side. Here, you do the mechanical work first, and due to this mechanical work, you generate the electrical energy. So this is the same thing happened in the hydel power projects. Over there here is a link to the hydel power project. You can click on that and you can watch on a video that what is going on, and especially in the Niagara Falls. So here is a water comes from the Niagara Falls, the water reservoir, and it falls over it, and then when it falls over it, so as a result, the water through the reservoir goes through it, and it rotates the rotator, and then the rotator is connected to the conducting coil, and which is placed in an external magnetic field, so the electricity is generated. Now the water which overflowed is going to the separate bay. So that is the outflow of the water. So you can use the water as well as you generate the electricity. Okay? Here is a control gate. You can stop generating the electricity. Right? Alright, so electrical turbine work on this principle. Now we're done with this part. So here is another thing. So I do the mechanical work, and then I lighten the bulb up. Alright? So this is the same thing. I do the mechanical work. So this is the reverse of the electrical motor. Okay? So then I generate the electricity. So here is a coil and the magnets inside this area, right? So